This is Babitha, working as Assistant Professor in the Department of EC in Institute of Aeronautical Engineering. In this session, we are going to discuss the question bank solutions for the first module, that is diode circuits. So before going to the questions of diode circuits, what are the contents we have already studied in the case of diode circuits? We'll see now. So in this particular module, we discussed about the PN junction diode as well as bipolar junction transistor, about two devices we learned in this particular module. So in the case of PN junction diode, we have seen the construction and operation of the PN junction diode and the voltage current characteristics of the PN junction diode, and also we have seen the applications of the diode. While coming to the applications of the diode, we are having rectifiers, okay, and clippers, clampers. These all are the applications of the diode. So we have discussed different types of rectifiers: half wave, full wave, and bridge rectifiers, and also different clamping circuits and clipping circuits. These are the applications of the diode we have studied in the case of PN junction diode. So the second part of the first module is bipolar junction transistor. So in the case of bipolar junction transistor, also we have seen the construction and operation of the bipolar junction transistor, and also the different configurations, that is common base, common emitter, and common collector configurations of the BJT. And in order to operate this bipolar junction transistor, the different biasing circuits are required. So about that biasing circuits also we discussed, and the load line analysis of the bipolar transistor also we have discussed, and all the three configurations of the transistor we can utilize for the amplification. So the common emitter, common base, and common collector amplifiers also we have discussed. And in order to analyze the bipolar junction transistor circuits, the small signal analysis or else hybrid analysis of the amplifiers are required. That will also be discussed in this particular module. So in this module, we can expect the questions related to the diode and its applications, as well as transistor and its configurations, and also its small signal model, and different current relations also we can able to observe in this particular module. So while coming to the question types, how many types of questions we may expect here? It is part A belongs to the problem solving and critical thinking questions. These are some analytical questions mostly related to the problems. And part B is long answer questions. These are mostly theory questions with long explanation. That is nothing but for 7 marks, we can say, or problem solving also for around 7 marks. And the part C we are going to discuss is the short answer questions, like definitions and formulas, some circuits type of questions we can expect in the case of short answer questions. So first in this, I'm going to discuss about the problem solving and critical thinking questions of diode circuits or module 1. So in that, the first question is, this is related to the common emitter amplifier circuit, common emitter circuit here. So in this, they given all the common emitter amplifier elements. Those are the biasing circuit elements, as well as the different terminal resistance is also given, and along with that, the H parameter values also given. So from this, we need to find the current gain, input impedance, voltage gain, and output impedance of the given common emitter circuit here. So in order to solve this particular problem, first of all, we have to know the formulas of all these parameters of the transistor here. So this problem we already discussed in the problems on common emitter configuration session. Try to go through that. And for now, the formulas required to calculate those are current gain minus HFE by 1 plus HOE into RL, and the input resistance is HIE plus HRE into AA into RA, and the voltage gain is the ratio of current gain into load resistance by input resistance, and the output resistance we can calculate here as RS plus HIE by RS HOE plus damage. So these are the formulas required to solve this particular problem. If you substitute the given values in this formula, we can able to get the given parameters. So while coming to the second question, this is also a common emitter circuit, and here also the given all the values, the potential divider values, R1, R2 values, as well as the load resistance, source resistance, and output resistance, emitter resistance also given in the problem, and the related H parameter values also given. And in this case also, we need to solve all the amplifier parameters, that is current gain, AI, how much, and the input resistance, RA, how much we need to calculate, and the voltage gain, PV, as well as the output resistance, R naught, also we need to calculate here. This problem also similar to the previous problem. So in order to solve this problem, again we have to utilize the same formulas whatever I shown in the previous slide. So by substituting the given values in these formulas, we can able to find the asked parameters in the problem. So this problem also we discussed in the problems on complementary comparison session. And the third problem belongs to the common base configuration. So here the given the collector current value as well as emitter current value and as well as leakage current here. So what current will flow in the collector circuit of the transistor when connected in CE configuration with a base current of 30 microamperes. So in this particular problem, they given the common base parameters. Those are IC equal to 2.98 milliamps and the emitter current equal to 3 milliamps and the leakage current equal to 0.01 milliamps. So this same transistor, if we connected in the common emitter configuration, and how much amount of collector current is flowing, we need to calculate, and for that purpose the given base current value as 30 microamperes. So if we write the current equation in the common base and common emitter circuits, if we write the current relation, we can able to find this, or we can able to solve this particular problem here. So the collector current equation in the common emitter configuration is, that is beta into IB plus 1 by 1 minus alpha into ICB. Okay, so here from the given parameters we can find the beta value and we can find the alpha value, and ICBO is nothing but this value only, ICO value. So if we substitute all the values, we can able to find the collector current in the common emitter configuration. So this problem we discussed in the problems on common base configuration session. And next problem related to the rectifier, that is full wave rectifier here. So the full wave rectifier is delivering 50 watts to a load of 200 ohms. That is nothing but the PDC value given it is, the DC power given it is 50 watts, and the load resistance value is given it as 200 ohms, and the ripple factor is given it as 1%. So from this we need to calculate the AC ripple voltage. So how much AC ripple voltage we are getting from the rectifier along with the DC content. AC ripple voltage we can write it as V gamma RMS value. So here generally the ripple factor is nothing but V gamma RMS by VDC whole square minus 1 under root. So from this PDC and RL value we can calculate VDC value. So once we know that VDC value and we already know the ripple factor value, if we substitute these two values, we can able to find this particular V gamma RMS value, that is ripple voltage. So this particular problem we discussed in the problems on rectifier session. And next problem belongs to the diode here. So in this particular problem, they given we need to calculate here it as DC resistance, that is RDC, as well as AC resistance, RAC, of a germanium junction diode at temperature given it as 25,000 degrees Celsius, and also given the reverse saturation current 25 microamperes, and the voltage applied across the diode is 0.2 volts here. So generally, the DC resistance RDC directly we can calculate by VDC by IDC, or V forward voltage by I forward current here. So this VF value is given already. So I current, IDC current or I current we can calculate by using the formula I equal to I naught into e power V by eta Vt minus 1. So here I naught value is given. Eta for germanium is 1 it is. Okay. 2 for silicon. So eta value we need to substitute here it as 1, and from this T we need to calculate Vt, almost we will get it as 26 millivolts. So that value also we can substitute here. After substituting all these values we will get I. So this I we can substitute to find the RDC value. And similarly, to find the RAC value here. To find the RAC value here we have eta Vt by I plus I naught formula. So here also we have all the values. Eta is 1, Vt value 26 millivolts, I value just now we have, from this equation we can calculate I value, and I naught is given. So if we substitute all these values, we will get the RAC resistance. So if we remember these two formulas, we can able to find the DC as well as AC resistances of the PN junction diode. So this problem we discussed on the static and dynamic resistance problems of PN junction diode. And the next problem related to the bridge rectifier, that is belongs to the rectifiers, that is the one of the application of the PN junction diode. So in this case, though it is a bridge rectifier, it is having 4 diodes, that 4 diodes in the form of bridge we are connecting to convert the given AC signal into DC. So the forward resistance of this rectifier given it as 5 ohms, and the transformer secondary resistance RS is given as 5 ohms, and the secondary voltage Vs is equal to 30 Vrms here. Okay. So here to find the secondary value 30 into root 2 we have to perform here. So that one will give the secondary voltage Y. And next determine the DC output voltage, that is VDC equal to how much. And also given IDC as 200 milliamps. And also we need to calculate the ripple voltage, that is V gamma equal to how much. So from this one we need to calculate VDC value as well as V gamma value. So VDC for the bridge rectifier is 2 Vm by pi here. So from this Vs value we can calculate the Vm value here. Okay, after calculating the Vm value, if we substitute here, we can get the VDC voltage here. So the ripple voltage, again from the ripple factor formula we can calculate, that is ripple factor gamma equal to V gamma RMS by VDC minus this whole square under root. So if we know this formula, if we substitute all the given values, we can able to find the V gamma RMS RS or else ripple voltage of the given circuit. So this particular problem also we discussed in the problems on rectifiers session. And next, this problem also belongs to the rectifier application of the PN junction diode. So here it is the full wave single phase rectifier. So it is a center tapped rectifier, not the bridge rectifier. So the given rectifier is the center tapped full wave rectifier here. So in the case of a center tapped full wave rectifier, we are going to utilize only 2 diodes instead of 4 diodes, and the internal resistance of the diodes we are taking here as constant, and that values we are taking here it as 30 ohms. And the load resistance value is given it as 1 kilo, and the transformer secondary voltage is changing from 200 to 200 RMS voltage. So from this we need to find the DC voltage, DC current, as well as the ripple factor, the given problem. So from this secondary voltage we need to calculate the maximum voltage of the maximum input voltage provided for the center tapper rectifier. So once we know the Vm, we can calculate the VDC value, that is 2 Vm by 5. That is the formula for to calculate the VDC value. So once we know the VDC value, we can calculate the IDC, or else we can also calculate 2 Im by pi here. And how we can calculate the Im value? So Im value we can calculate by Vm by Rf plus RL here. So this is the internal resistance of the diode as well as load resistance of the diode. Sometimes they may also give the secondary resistance of the transformer also. In that case, we need to add the RS resistance to find the Im value here. So from this we will get the Im value. If we substitute that Im value, we will get the IDC value. So ripple factor, once we know these two values, we can be able to find the ripple factor of the given circuit. So this particular problem also be discussed in the problems on rectifier session. And next problem belongs to the full wave rectifier. Again it is. So it is also a center tapper transformer with two diodes, and the secondary voltage given it as 100 to 100 volts. That is RMS voltage only. Once it is giving it as a secondary voltage means it is the RMS voltage only. Once it is mentioned as maximum voltage only, directly we have to take it as the Vm voltage. If it is given it as secondary voltage means we have to multiply with root 2 to find the Vm voltage. And each one of the diode is rated at I maximum. So the Im value is 400 milliamps and the IDC value is 150 milliamps, and neglecting the voltage drop across the diodes. Solve the value of the load resistance that give the largest DC power output. There is nothing but how much load resistance is required here, and VDC voltage, and also IDC current across the load resistor, and the peak inverse voltage of the diode we need to calculate here. See, once to calculate the VDC voltage, the formula here it is 2 Vm by pi in the case of a full wave rectifier. So here to find the Vm value, from this we can find the Vm value. This 100 into root 2, if we perform, we will get the Vm value. So that Vm value, if we substitute here, we will get the VDC value. So once we get the VDC value, we can directly find VDC into RL, or else we can also find by using 2 Im by pi. And again Im we can calculate by Vm by RL value. Okay, Vm by RL value or internal resistance of the diode. So if you substitute that, you will get the IDC value. So once we know the IDC and VDC value, from that relation we can find the RL value. And peak inverse voltage of the center tapper transformer here it is 2 Vm. So it is Vm here. Why? Because even though we are utilizing two diodes in the case of center tapper transformer, but each cycle only one diode is in conduction mode, one more is in reverse bias condition. So how much maximum voltage which is present across the reverse biased diode indicates the peak inverse voltage of the rectifier. So in this case, during the positive half cycle, one diode is in the conduction mode. During the negative half cycle, one more diode is in the conduction mode. So at a time only one diode is in the conduction mode. So the maximum value at that particular diode is the peak inverse voltage, and that is equal to how much we are getting here. So in this way we need to calculate this type of problems. And this problem we already discussed in the problems on rectifiers session. And this problem related to the half wave rectifier. Okay, and they given the load resistance value as, so it is ohms. The load resistance value given it as 1000 ohms, and AC voltage given it as 325 volts peak value. So peak value is nothing but it is Vm only directly given. So the RF value is given it as 100 ohms. Here it is 100 ohms. So here we need to find the peak value, the maximum value of the current, and the IDC current as well as IAC current, and also we need to calculate PDC, how much DC power we are getting, and how much AC power we are getting, and how much efficiency of the half wave rectifier. So here they directly given the Vm value. So from this Vm value we can calculate the Im value. So the Im value is Vm by Rf plus RL here. So if we substitute that value, we will get the Im value. So that is the Im value. And to find the IDC, the formula is 2Im by 5. Okay. And to find the AC value, that is, we will get it as Im by root 2 here. So once we know the Im value, we can calculate IDC as well as IAC values. And PDC is nothing but IDC square into RL, or else in terms of VDC square by RL also we can take. And PAC is equal to IDC square into RF plus RL. If you have any secondary voltage, we have to take that one also into consideration. Sorry, IAC here, IAC square into RF plus RL. And to find the efficiency, that is PDC by PAC into 100%. So if we substitute all the given values in these formulas, we can able to find all the asked parameters in the given. So this problem also we discussed in the problems on rectifiers session. And the next problem related to the transistor, bipolar junction transistor. So in the case of bipolar junction transistor, the given base to emitter voltage VB as 0.7 volts, and the current amplification factor of common base configuration is given alpha, that is 0.98, and the collector cutoff current is 10 microamperes, and they given the collector resistance as 2 kilo ohms here, and VCC, the supply voltage, given it as 12 volts, and the base current is given it as 10 microamperes. So from these we need to calculate beta value and the ICEO value, that is the reverse saturation current in the common emitter configuration, and the collector current as well as emitter current as well as collector to emitter voltage here. So in order to find all these values here, we have to take the circuit of the transistor, and we have to apply the KVL and KCL equations to solve this. So here beta value directly from the relation beta equal to alpha by 1 minus alpha. So here alpha value is given. If you substitute that, you can find the alpha value. Okay. And to solve the IC here, so IC equal to beta IB plus 1 by 1 minus alpha into IC. So here we have beta value, IB value, alpha value, and IC value also given. If we substitute all these values, we can able to find the ICEO value. And IE is nothing but what? IE is nothing but IC plus IB here. Okay, IC plus IB here. So here we know the IC value as well as IB value. If we substitute that, we will get IC plus VB. To solve this VCE, we have to take from the circuit VCC minus IC into RC. So VCC is given, the supply voltage 12 volts, and the collector current is given, and the collector resistance is also given. So if you substitute all that values, we can able to find the collector to emitter voltage here. So this problem we discussed in the problems on common emitter configuration session. So till now we discussed the critical thinking or analytical reasoning related questions. So now we are moving to the part B, that is long answer questions. So we need to write in detail about ask each and every concept in this particular questions. So in this case, the first question is outline the VI characteristics of the PN junction diode for forward bias and reverse bias voltages and represent the static and dynamic resistance of the diode in the characteristic curve. So to write the solution for this given question, the first thing is we have to write about the construction of the PN junction diode, and next working of the PN junction diode, and next we need to go with the VI characteristics of the diode by applying the forward and reverse biasing, and after drawing the VI characteristics we need to calculate the static resistance as well as the dynamic resistance. So these are the points we need to cover in this particular question. So while coming to the construction, that is formation of a diode. So to form a diode, we have to consider two pieces of semiconductor materials. One is P type of semiconductor material and one is N type of semiconductor material. So this is the P type of semiconductor material. So in the case of P type of semiconductor materials, more number of holes are present. Those are the majority charge carriers of the material. And similarly, we have to consider the N type of material. So in the case of N type of material, the electrons are the majority carriers. So that's why we are indicating with the green circles. Here we are indicating with the white circles. So if you join these two pieces of P type of semiconductor material and N type of semiconductor material, so there is a junction formed between two materials. So after, as soon as once we join the two type of materials, the electrons will try to diffuse from P side to N side, and the holes also trying to diffuse towards the P type to N type here. So what is the electron which is leaving from this N type region and combining with the hole which is present in the P type of material, that become the negative immobile ion. So because of the movement of the electrons from N region to P region creates the negative immobile ions in the P region across the junction. And similarly, so once these holes which are moving from P region to N region and those are combined with this particular electrons, that loses its positive energy and that becomes the positive immobile ions here. So because of this diffusion process, more number of positive and negative immobile ions are formed across the junction. So that particular region we are calling it as the depletion region here. So once the depletion region is formed, means there is no movement of charge carriers from P to N side and into P side here. So this is about the formation of the diode. And next, coming to the working. So in order to see the working of the PN junction diode, so first of all we are taking the forward bias condition of the diode here. So in the forward bias condition for the diode, we need to apply P type material to the positive terminal of the battery, and the N type is applied to the negative terminal of the battery here. So I have considered the PN junction diode as it is here. So the P type of material I have connected to the positive terminal of the battery, and the N type of material I have connected to the negative terminal of the battery. So here we need to explain about what is the process going on once we apply the forward bias to the diode here. So the holes which are present in the P type of material are coming away from the junction, coming away from the battery, and those are moving towards the junction. And similarly, the electrons which are present in the N type material are also repel from this negative terminal of the battery and they are moving toward the junction. So the movement of the electrons and holes are diffusing towards the PN junction diode. So the depletion region width will be decreased here. So once the depletion region width is decreasing means the movement of charge carriers will be increased. So there is a flow of forward current in the diode here. So in this case we will get the characteristics the VF versus IF, that is depends upon how much amount of voltage we are providing here. So till cut-in voltage, okay, till V gamma, there is low rise of current here. After V gamma, there is a sudden rise of the current here. So here V gamma or cut-in voltage is nothing but the voltage required for the diode to make into more conduction or to more flow of current in the device. So this is about the forward bias condition of the diode. And next we'll coming to the reverse biased PN junction diode. So in the case of a reverse biased PN junction diode, the negative terminal of the battery is connected to the P region and the positive terminal of the battery is connected to the N region. So because of this process, the poles which are trying to attract towards the negative terminal of the battery, and here also the electrons are trying to attract towards the positive terminal of the battery. So because of this, the length of the depletion region still it will be wider. Okay, the depletion region width will be increases. So once the depletion region width is increasing means, so the movement of charge carriers will be less. So there is no current will flow in the device. So only some little amount of current, that is reverse saturation current due to the minority charge carriers will be flowing in the device. So in this particular case, we will get the characteristics of VR and IR in this. So slowly it will increase after it will rises suddenly. So this will occur, sudden rise of the current will occur once the breakdown voltage, the reverse voltage reaches to the breakdown voltage of the diode here. So this thing we need to explain in the reverse bias characteristics. So next, if you see the VA characteristics combined in the forward bias as well as the reverse bias. So actually the PN junction diode will operate in the three biasing regions, that is the zero bias condition, forward bias condition as well as reverse bias condition here. In the zero bias condition, the formation of the depletion region will be done. There is no movement of charge carriers, so that there is no flowing of current in the device. Only in the forward bias we will get the huge amount of current. In the reverse bias case, we will get only small amount of the reverse current. So that forward and reverse characteristics I have taken combinedly here. So this is the VA characteristics of the PN junction diode. And next we have to find the static and dynamic resistances from the VA characteristics of the diode. So here the static resistance is nothing but the DC resistance of the diode and the dynamic resistance is nothing but the AC resistance of the diode. So this static or DC resistance we can calculate at any one operating point of the forward bias characteristics of the diode here. So this is the forward region and this is the forward bias curve. So here suppose I am taking any one point here. So at this particular point, how much voltage VF is there and how much current IF is there. This is VF and this is VR here. Okay, so this voltage and this current will give the RDC or static resistance, that is the ratio of VF by IF. Okay, this value will give the DC resistance. And while coming to the dynamic resistance of the diode. So to calculate the dynamic resistance, here we have to take the minimum 2 points on the operating point of the forward characteristics of the diode. Why? Because the dynamic resistance will indicate the variation of the current with respect to the variation of the voltage. So for that purpose, I am taking 2 points here. So for these 2 points, how much variation of voltage will be there and what is the corresponding variation of current will be get. So to calculate that AC resistance, here we have to take 10 VF by del IF. Okay, here this is the maximum value and this is the minimum value, and here also it is the maximum value and it is the minimum value. So here we can write it as V maximum minus V minimum, right? I maximum minus I minimum will give the AC resistance from the characteristics. So generally directly also we can calculate the DC and AC resistance by utilizing the formula, but here from the characteristic curves we are calculating the AC resistance, and this both the DC resistance as well as AC resistance we can also calculate in the reverse biased PN junction diode or by utilizing the reverse characteristics of the PN junction diode. So in this way we need to explain the construction operation of the diode and the VI characteristics of the diode and also the finding of the resistances. And next one is illustrate the transition capacitance and diffusion capacitance with suitable expressions here. So in this case, this transition capacitance and diffusion capacitance we already discussed in the diode capacitance session. So this transition capacitance will exist in the reverse bias PN junction diode. Here transition capacitance will exist in the reverse biased PN junction diode, and the diffusion capacitance will exist in the forward bias PN junction diode. So in both the cases, these capacitance values are variation of charge with respect to the applied voltage here. And always the capacitance value is inversely proportional to the width of the depletion region, that may be in the forward condition or that may be in the reverse condition. So we need to derive the expression for this transition capacitance as well as diffusion capacitance in the forward bias as well as the reverse bias by considering the width of the depletion region and the voltage current relations. And always the diffusion current value is far greater than the transition capacitance value here. So in this way we need to explain what is meant by transition capacitance and how it is existing in the reverse bias condition, and what is meant by diffusion capacitance and how it is existing in the forward bias condition here. So this transition capacitance value is less. Why? Because in the reverse bias condition the depletion region width is very high. So once the width of the depletion region is very high means the transition capacitance value is very low. But in the case of diffusion capacitance, once it is existing in the forward bias condition, so the depletion region width is very less in the forward bias condition. So that's why this value is very high. And next, explain the operation of the PN junction diode under forward bias and reverse bias condition, and sketch the VI characteristics of the PN junction diode. So in this case also, we need to write the points, the construction of the diode. Just now in the previous slides I have explained, and also the operation or working of the diode in the forward bias condition as well as in the reverse bias condition, and also we have to draw the VI characteristics in the forward bias as well as in the reverse bias. So this is the formation of the diode. You need to explain how we are taking the p-type and n-type materials and how we are forming the junction and how the depletion region is forming. And next, in the forward bias condition, how we are applying the battery levels and how the current level is changing by varying the VF voltage. And similarly, in the reverse bias condition, once we change the polarities of the battery, how the operation is changing and how the reverse current is changing, we have to explain here. And after this, we need to explain about the VI characteristics of the diode. And next, what is rectifier efficiency? Derive expression for the half wave rectifier and full wave rectifier. So generally, this question belongs to the rectifier, that is the application of the PN junction diode. So the rectifier efficiency is always the DC power PDC to the DC power PDC to the AC power PAC. Okay, almost in the case of half wave rectifier, we will get this value as 40.6% if we calculate this. And in the case of full wave rectifier, In the case of full wave rectifier, almost 80% we will get this particular value. So in order to derive the expression for this, we have to calculate the DC power as well as AC power and substitute that values here. So in the case of half wave rectifier, PDC equal to IDC square into R, and IDC is nothing but Im by 2 whole square into R, and PAC is nothing but IAC square into RL plus RF plus RS. How many resistances are there? That many we have to take. So here IRS is nothing but IAC is nothing but Im by pi here. So Im by pi whole square into RL plus RF plus RS. So if we substitute these two values here, we will get the half wave rectifier efficiency. Similarly, in the DC power as well as AC power in the case of full wave rectifier is different. In that case also we need to solve like this PDC and PAC values. If you substitute that, we will get this particular thing. So this about this we already discussed in the full wave rectifier as well as half wave rectifier analysis session. And next, find the terms as referred to the full wave rectifier, that is peak inverse voltage, transformer utilization factor and the ripple factor here. So in the case of a full wave rectifier, the peak inverse voltage, in the full wave rectifier, the peak inverse voltage is the maximum voltage how much we are providing for the diode. Why? Because in the case of full wave rectifier, at a time only one diode is in the active condition or in the forward bias and one more diode is in the reverse bias condition. So once how much voltage which is existing in the reverse bias diode is the maximum voltage, that is the peak inverse voltage of the diode, and also we have to calculate the transformer utilization factor, that is depends upon how much efficiently the transformer we are utilizing for converting the AC into DC form. So that's to calculate this we have to take the AC rating of the transformer as well as AC power, DC power of the transformer. So then we need to find this transformer utilization factor. And next, ripple factor gamma. So ripple factor gamma indicates how much amount of AC voltage or current which is present across the output of the rectifier. That may be in the half wave or full wave. We are discussing about the full wave rectifier. So it is almost, we will get it as 0.48 if we calculate this. That is the ratio of AC content to DC content. So this one also we discussed in the analysis of the full wave rectifier. And next one is list the merits and demerits of half wave, full wave and bridge rectifier. So while coming to the advantages of the half wave rectifier, it is the simple circuit. Why? Because to construct this we require only diode as well as the resistor, and it has very low cost. Why? Because the cost of the resistors as well as diodes are very less, and we can easily utilize this particular circuit and we can easily construct this particular circuit, and it has less number of components, so it is very cheap. So these are the advantages of the half wave rectifier. So while coming to the disadvantages of half wave rectifier, here the transformer utilization ratio is very less. Here why? Because the efficiency we are getting is only 40% in the case of half wave rectifier. So that's why we are telling that transformer utilization ratio is very less, and it produces very less output voltage. And the DC saturation of the transformer core resulting in magnetizing current and also some hysteresis losses and generation of harmonics here. And the output power as well as efficiency are quite low here. Only 40% efficiency it is provided. And power, why we are getting very less here means the power delivering to the load is only during the half cycle of the applied input signal. So because of that reason we are getting very less efficiency. And ripple factor we are getting very high. Why? Because almost 1.21 in terms of percentage, if you write 121% of AC content only we are getting along with the DC content in the case of half wave rectifier. So that's why the ripple factor is very high. That is the disadvantage. And it allows only half cycle throw per sine wave, and the other half cycle is wasted here. So this leads to the power loss in the device. So these are the so many disadvantages of the half wave rectifier. In order to overcome these disadvantages only, we are moving for the full wave rectifier. So in the full wave rectifier, we are having two types: center tapped full wave rectifier and bridge rectifier. So in this case, the ripple factor is much less than that of the uh, half wave rectifier. Here it is almost 0.48 only. So from the 1.21, it is reduced to 0.48 here. And the DC output voltage, DC load current values are double compared to the half wave rectifier. And the efficiency of this one also doubled, almost 80% we are getting, but in the half wave rectifier only 40%. And the output efficiency is high because the AC supply delivers power during both the half cycles. So that's why efficiency also very high. And next, well, coming to the disadvantages of center tapped full wave rectifier, it is expensive because of center tapped transformer we are utilizing, and the output voltage of the secondary voltage of each diode utilizes only one half of the transformer secondary voltage. So it is difficult to locate center on the secondary winding of the transformer, and the peak inverse voltage of the diode gives twice that of the diode used in the half wave rectifier. So the diode must be have high peak inverse voltage. And while coming to the advantages of the bridge rectifier, so these are the different advantages of the bridge rectifier. It is not utilizing the center tapped transformer, and the no output terminal is grounding here. The transformer utilization factor is also high, and no step up or stepping down of the AC voltage is required here. And here we are not using any center tapped transformer, so only bridge is suitable for this. It is required, the transformer is less costly as it is required to provide only half of the voltage of an equivalent center tapped transformer. And the transformer utilization factor is high, and for high voltages applications we can utilize this. And while coming to the disadvantages of the bridge rectifier, so these are the advantages of the bridge rectifier over a center tapped transformer. And the disadvantages of the bridge rectifier, it requires two extra diodes, and two diodes are in series, those are conducting in alternating half cycles. This creates a problem when low DC voltages are required, and the resistance, internal resistance voltage drop is twice that of the center tapped circuit, and stepping up as well as stepping down of the voltage is not needed. We may even do without a transformer. So these are the disadvantages of the bridge rectifier. Even though we are having different advantages and disadvantages, we are utilizing these are for different applications. And next one is this is the problem related to the half wave rectifier. This problem we already discussed in the half wave rectifier problems section. And this is the full wave rectifier problem here. The given load resistance as well as the load, they given it as VDC current, VDC power as well as load resistance. We need to find the AC ripple voltage. In the previous slides we discussed this problem, and also I covered this problem in the problems on rectifier session. And next, explain the working of two-level diode clipper with the circuit diagram and waveforms here. So this is the two-level clipper, that is nothing but it is going to clip the positive half cycle of the circuit as well as negative half cycle of the circuit. So we have to take one half cycle and we have to see the operation of the diode, whether it is in the on state or off state. Depending upon that, we will get the output voltage. And similarly, we have to take the negative half cycle of the circuit, and next we have to see the status of these two diodes, and then we have to observe the output voltage. So we have to explain the each and every point clearly. Okay. And illustrate the positive clamper circuit operation with the need switches. So the positive clamper means it will shift the level, DC level of the given waveform to the positive direction. So here we are having two types of positive clamper with positive VR and the positive clamper with negative VR here. So this is the positive clamper circuit with capacitor and diode we are performing here. So the clamping means shifting the signal to the above or below the reference level. So here the positive means the total signal is shifting towards the positive direction. So here we have to take the positive half cycle as well as negative half cycle, and we have to see the status of the storing, charging and discharging levels of the capacitor as well as the diode on off conditions. According to that, we need to write the output voltage equation. Then we need to draw the output waveform. And positive clamper with positive VR means, so along with these two components we are adding the positive reference voltage. So the operation is same here. In this case also, uh, instead of only input voltage, we have to take both the input voltage as well as the reference voltage to explain this particular circuit. And in this case also, instead of shifting from zero level, after the reference voltage the signal is shifting. That is the difference. And next one is positive clamper with negative resistance, negative voltage means, here we are providing the reference voltage as negative, so the signal is shifting towards the negative direction. And next, explain the formation of depletion region in open circuited PN junction diode with needs switches. So this will also be discussed in the previous slides, how the PN junction we are forming and how the depletion region is forming in the PN junction diode. And next, in the common base connection, this is the common base configuration problem. This we discussed in the common base configuration session. We have to find the DC current. Okay, DC current gain, beta, how much we are going to get. And next, demonstrate the working of transistor in common emitter configuration and draw its input-output characteristics. So in this particular question, we need to explain how to construct the common emitter amplifier and what is the operation of the common emitter amplifier and what are the input characteristics and what are the output characteristics of the common emitter amplifier. So here I am showing the common emitter amplifier. So the emitter terminal is acts like a common between the base and collector terminals. Okay, so here we need to provide the biasing to operate that particular circuit. We are providing the voltage division or potential divider biasing to operate this circuit. Okay, and after that we need to find the proper Q point to operate in the amplifier mode. So the Q point is in the active region, then only we can able to operate the transistor in the active region. And these are the input characteristics of the common emitter amplifier, that is VBE versus IBE when VCE is equal to constant. That is nothing but different values of VCE. We have to make it constant and we have to vary the VBE voltage. The corresponding IB current will be increases. These are similar to the characteristics of the forward biased PN junction diode. And similarly, the output characteristics of the CE configuration. So these are between VCE versus IC when the base current is constant. So we are maintaining different constant base currents and we are varying the VC voltage. We are getting the different IC current. By utilizing that, we are drawing these waveforms. And show the H parameter of a bipolar junction transistor in small signal model. So the H parameters are nothing but the hybrid parameter, that is the mixing of voltage and currents here. So these H parameters, to calculate these H parameters, we have to take the two-port network. Our transistor is also forming a two-port network. Why? Because it is having three terminals. One terminal we are taking it as the common. So input side two terminals and the output side two terminals. And it acts like a linear circuit. And the input side we are having the input voltage and current, and the output side we are having the output voltage and current. So every transistor we can represent in the hybrid equivalent circuit in this way. So to draw this circuit, we have to calculate all the H parameters, H11, H12, H21 and H22. So to calculate these H parameters, I am taking this particular relation. So here to calculate H11, V2 must be 0 here. If V2 must be 0 means V1 by I1, V2 equal to 0. So this one we can call it as HI, input impedance. And next we can calculate H12 parameter. So H1 is nothing but V1 by V2 whenever the input current is open circuit, I1 is equal to 0. So this is the reverse voltage gain. Reverse voltage gain. And next we can calculate H21. This is the first equation. This is the second equation. So H21 is nothing but I2 by I1 whenever V2 equal to 0. So this is HF, that is forward current gain. And next H2, that is I2 by V2 whenever I1 equal to 0. This is output admittance. So once we find all these parameters, we can draw the H parameter equivalent circuit. So this is applicable for all the types of configuration, that may be CE or CB or CC. The subscript will be added in all the parameters. And next, explain the DC and AC load line analysis of the BJT. So if the load line is drawn only when the DC biasing is given to the transistor and there is no AC signal is applied, means that is the DC load line. But the same load line, when we apply the AC signal as the input, what is the curve we will get? That is the AC load line. So this is the DC load line. Okay, this is the DC load line. We are providing the DC voltage as well as the current. And this is the AC load line whenever we are providing the input as the sinusoidal signal. So each and every point we need to explain clearly at what input, what is the characteristics we are getting. And next, this is the problem related to the common base amplifier circuit. We have already discussed in the common base problems and common base comparison session. And next we have current gain of the transistor we need to calculate here. So this problem we discussed in the problems on the transistor. And next, examine the validity of approximate hybrid model applicable in low frequency range. That is nothing but how we can able to utilize this hybrid model in the low frequency region. Why? Because the AC low frequency model is nothing but this is for AC signals only. The DC signal must be same. So AC signals means the frequency level is very, very low. So that's why hybrid parameter model is applicable for only low frequency signals. And illustrate the common collector configuration of BJT with relevant figures and explain its input-output characteristics. So here first we need to explain the operation of the common collector amplifier here. And this is the common collector amplifier. The collector terminal acts like input and output here. And these are the input characteristics of the common emitter configuration. And the output characteristics we will get it as VCB versus IE here. So we will get like this the different characteristics whenever the base current is some constant, 10 microamps, 20 microamps, and 30 microamps, and 40 microamps. So in this way we have to draw the output characteristics. And next, draw the small signal model of common base BJT amplifier. Derive the expression for voltage gain, input resistance, current gain, output resistance. So for that purpose, we have to consider the common base BJT amplifier and what is the operation of that one. And by taking the equivalent circuit, we have to find the voltage gain, that we will get it as this much. And similarly, the current gain, that is the ratio of output current to the input current. Okay. And next, the output resistance, we will get it as almost the collector resistance. So we need to write the each and every step clearly in this. Why? Because it is the long answer. The next one is short answer questions. So in the short answer question, define depletion region. This depletion region will exist in the EM mentioned about once the P type of material as well as N type of material are connected together here. Okay, because of the movement of charge carriers into the opposite direction, there is a form of depletion region in the circuit. And next, list the applications of the diode. So this diode can be utilized as a photodiode, okay, in the reverse bias condition, and it is also utilized for the solar cell. And most of the cases in the forward bias we can utilize for the light emitting diode applications. And next, list the differences between the ideal and practical diodes. So in the ideal, diode acts like a perfect conductor and perfect insulator, but in the practical current, it does not act like a perfect insulator or conductor here. Ideal diode draws no current when it is in the reverse bias condition, but the practical diode will draw some current whenever it is in the reverse bias condition. So ideal diode offers infinite resistance in the reverse bias condition, but the practical diode will offer very high resistance in the reverse bias condition, and it cannot be manufactured by, because we are idealism, we are assuming some conditions. According to that, we will design the practical one. So that's why this can be manufactured here. So it is zero cut-in voltage. It is having low cut-in voltage, and the ideal diode has zero voltage drop across its junction whenever it is forward biased, and it is having very low voltage drop when it is in the forward bias. So it acts like a perfect conductor and insulator, and it is does not act like a practical conductor or perfect conductor or insulator. And next, outline the VA characteristics of the PN junction diode. So this is in the forward bias condition, this is in the reverse bias condition. So we need to explain some 2 points related to the forward bias and 2 points related to the reverse bias here. And next, explain drift current in PN diode. So drift current is occurred whenever the no bias is applied to the junction here. So because of the diffusion process only, because of the diffusion current which flow from H to P region to N region and N region to P region, it exactly balanced by the equal and opposite drift current here. Okay. The next one is define efficiency and outline the efficiency of half wave and full wave rectifier. So in this case, we need to explain about what is meant by efficiency and how much it is for half wave and full wave rectifier. Always efficiency is the DC power to the AC power. So we need to calculate the DC power as well as AC power equations, so that in the half wave rectifier, the maximum efficiency we will get it as 40.6. We need to derive it. And in the case of full wave rectifier, we will get it as 80% for full wave rectifier. And next, illustrate the load line analysis of the diode here. So in the case of diode, if you draw the VF as well as IF at one particular point, if we find the values, the Q point values, this is the Q point. So how to calculate these two values? You have to derive here. And next, how diode acts as a switch here. So here in this case, we have to take the diode with the resistance. We are applying some input voltage and we will get some output voltage here. So if this input voltage is VI is applied, means the diode is in the forward bias condition, so it acts like a closed switch. Okay, if the input voltage is negative value, so in that case the diode will be in the reverse bias condition, so it acts like a open switch here. So in this way, depending upon the input voltage, how much we are applying, the diode will act like a open switch as well as closed switch. And now let's show the circuit of half wave rectifier using PN junction diode. So in the case of our rectifier, we are having one transformer, okay, and we will connect one diode, and we will measure the output voltage. Output voltage V1 here. So this is diode V1. Here we are applying the 230 volts AC. So this is the circuit of the half wave rectifier. And next, list the types of the rectifiers. So here 3 types of rectifiers are there. Those are half wave rectifier and full wave rectifier, and third one is bridge rectifier. Okay. So just you need to give one point related to these rectifiers, how we are forming here. And next, show the circuit of positive P clipper using PN junction diode. So this is the circuit of the positive P clipper. So it can clip the total positive P. So in the output only we will get the negative half of the signal. And next, what do you mean by clamper? So clamper is a circuit. It will be used to shift the waveform once it is in the origin. So this will be shifted to total above the horizon, or else it will shift total below the horizon. So it will clamp above or below the reference voltage. So that is the basic function of the clamper, that is shift the DC level of the C. And next, show the bipolar junction transistor and label the terminals of transistor. So here this is the bipolar junction transistor. This is the base, collector, emitter. So this is the NPN transistor. And one more type of transistor we are having here, it is base, collector, emitter terminals. But here the current direction is towards the junction, it is PNP transistor. And next, show the Q point in transistor characteristics. So to show the Q point, we have to take the output characteristics. For example, I am taking the common emitter amplifier characteristics, that is VCE versus IC, and the base current is some constant value here. IB equal to 0, IB equal to 20 microamperes, and IB equal to some 40 microamperes, and so on. So when we find some 2 points on the collector current and we see this is the VCEQ value and this is the ICQ value, if we, after finding these two values, if we join these two lines, and wherever this Q point is cutting the characteristics of your transistor in the active region, that is the Q point of the amplifier. Why we are considering the active region means in the active region only the transistor acts like an amplifier. And next, relate alpha, beta and gamma in the bipolar transistor. So here alpha equal to beta by 1 plus beta, and beta equal to alpha by 1 minus alpha, and gamma equal to 1 plus beta or else 1 by 1 minus alpha. So this is the relation about alpha, beta as well as gamma in bipolar junction transistors. And next list out the H parameters in CE configuration. So in the CE configuration, we are having HIE, HRE, HFE as well as HOE parameters. So this input impedance is between the VBE by IB whenever VCE equal to 0. Reverse voltage gain means VBE by VCE whenever the IB current is 0. Forward current gain means IC by IB whenever VC equal to 0. Output admittance means output current by input current, output current by input voltage VBE. So that is nothing but VC whenever IB equal to 0. So this is the output admittance in the case of CE configurations, and these are the H parameters in the CE configuration. And next, outline the output characteristics of NPN transistor in common emitter configuration. We have already drawn this. This is the VCE versus IC curve with base current is some constant value. So base current from 0 to some 20 microamperes. So it will increase like this. So these are the output characteristics of the NPN transistor. And next, show the relation between IC beta, IB and ICBO in bipolar junction transistor. So we can write ICEO equal to beta. So the collector current in common emitter configuration is equal to beta IB plus 1 by 1 minus alpha into ICB. Okay, so this is the relation between all these values. And next, what is the significance of the arrowhead in the transistor symbol? So in the transistor symbol, this arrowhead indicates the current direction. Current direction. And next, show the current amplification factor in CE configuration. In CE configuration, this is theta. It is the ratio of collector current to base current. So in this session, we have discussed the questions and related solutions as well as the problem, as well as answers related to the module 1, that is diode circuits. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.